Thank you. So it's been a great series of talks so far. I'll be focusing somehow on fMRI, I think like the previous talk, and so trying to repeat what are the main points, the main issue that with current procedures, and how to avoid some pitfalls in the interpretation of these models. Okay. So MVPA has become popular, as you know, because it is known to be or supposed to be more powerful than standard brain mapping procedures like the classical SPM framework. We have to clarify what this means, so I'll get back to that later. I think another point which has not been discussed so much this morning is that it allows you to generalize across protocols. When you learn to discriminate between A and B, and you can generalize this discrimination to C versus D. This means that you have captured some commonalities between A and C on the one hand and B and D on the other hand. And this is very interesting, I think, for brain mapping or for cognitive applications of MVPA. Also, another point for population studies, group studies, is that you can make individual prediction or like for diagnosis, which you cannot do with standard statistics. So in this talk, I will first get back to the very simple sample size issues in MVPA, which have been discussed this morning in the framework of cross-validation. And then I get back to interpretation issues and functional specificity. So my first point is not about brain imaging, it's about machine learning in general. In machine learning, you try to learn models from data. You don't know the model a priori, you try to learn it from the data. So you need data, that's obvious. And so the first point when you try to do machine learning, and it's for any kind of application, if you have less than 50 samples, you should just do something else. An example on a practical example to illustrate this. Let's look at the effect of age on gray matter density. It's a huge effect because we know that we can predict age with gray matter density pretty accurately. Actually, that's what I'm doing here on the OASIS dataset. So I'm just changing the size of the learning set. So I increase the value from 10 to 300. And you see that the accuracy of the prediction measured by the R-square increases, of course, with the sample size because you've got more power to detect the effect of age on gray matter density. So actually, the effect is so strong that even with 10 subjects, you can get something which seems to be better than chance, which is impressive. But of course, you increase the reliability of your experiment with like a 10-fold cross-validation. Actually, no, I used all the remaining set as a test set, so we have a rather large test set in that case. So we increase the reliability of the model with when we increase the sample size. And especially, you see that it starts to stabilize somehow after 100. But below 100, you are really quite far from the best value. But this was the easy part. Now the difficult part is you want to get a discriminative map from this classifier. And the point is, if you do that just with different groups, by sampling different groups in the population, you just end up with different patterns. And here the variability is quite impressive in that case. But you're just asking the same question, just with slightly different data. So to characterize this a bit more, what I've done was just to take the mean of the groups. You obtain an average pattern, which actually looks a bit better than the patterns from different groups, and also the variance. And so from the mean and variance, you can compute a kind of effect size map, which is the mean divided by the standard deviation, that tells you in which region there is some consensus across the group for a positive or a negative effect. And so in that case, due to the large variability, you see all the map is a bit in the green color, so close to 0, which means that any of these draws is not a good representative of all the possible draws from this population. And of course, if you increase the population size from 10, 20, 50 to 100, so you start to see that you've got much more signal. These larger values mean that if you take one group of 300 subjects, you might reproduce it quite well with another group of 300 subjects sampled from the same population. And it's even more important if you use deep learning. So deep learning is becoming popular, but the sample complexity of deep learning is just much larger than this. It's a simple, SVM. It's a linear model. If you go to deep techniques, you probably need not hundreds, but thousands of samples. Okay, now let me switch to the second point, interpretation of pattern maps in MVPA. So there are two types of opinion. So people claim that this boosts the sensitivity of your analysis, which is the optimistic point of view, and people who say that the decoding patterns should not be interpreted as activation patterns. So these are different claims. Actually, both are true to some extent, just they need to be clarified. I think the main bits of reasoning in between are that, first, when you have accurate decoding from some signal, it just rejects a global null hypothesis on the whole region or the whole brain that you have used. So it's kind of a simple problem. If you were doing like classical SPM mapping, you could do a global F-test over large voxels, large regions, and it would be kind of the equivalent. But it's hard to do. Localization with a decoding procedure is a nil-post problem. I will discuss that in detail later. And maybe a way to get into this is to think that when you look at the pattern map for a classifier, it represents the conditional evidence of one voxel being involved in the prediction, given all the other voxels. While classical SPM, like SPMT maps that you would generate, they measure the marginal evidence. Is this voxel associated with the target information Y? So let's review this a bit more in detail now. So the multivariate miracle occurs so when you have several voxels, which would be hard to analyze with classical means, but when you take them together, you can predict very accurately the target. And so the perfect scenario has been described by in this nice paper by Heinz, in which you just take one voxel with noise and another voxel with the same noise plus a very little bit of signal. So if you look at each voxel in particular, from the histogram of activity in each voxel, it's hard to disentangle the two classes. But when you just do the subtraction voxel 2 minus voxel 1, you have an almost perfect separation. So this is the perfect case for MVPA. But it's a configuration that is a bit unlikely because this means that all the structure would be in the noise that would be replicated exactly across voxels, while the signal would be very isolated in some voxels, which does not seem a very realistic scenario to me. It can be true to some extent because you can have motion patterns that are actually similar across different voxels, but still. And of course, it's also time to recall that you should always try to clean your signal. Even when you do MVPA, we should make sure that we have a good pipeline for data pre-processing. Okay, now let's look at the downside or the other side of the coin. And here I take the argument from Stefan Hofer. And to explain this, I have created a simulation where you've got a brain map, which is a square in that case, and the true pattern is a region negatively or positively associated with the target information. Now just put some correlated noise on top of that and it'll generate some samples. So you can, then when you analyze them, you can do a T-map, like an SPMT mapping, and it would recover actually quite well the two squares in that case. Now, if you try to do the same thing with a support vector regression, for instance, or rich classifier, so you end up with these very ugly patterns with actually, for instance, for the red square, you've got this red voxel in the middle, surrounded by blue voxels, because essentially it's like in the Heinz scenario where you have the surrounding voxels have the same noise, more or less, because the noise is very correlated. And so you just need to learn how to subtract the signal from this region from the outer region. And this is a very good classifier. But of course, it's far from the true pattern. And if you use a sparse model like the lasso, it avoids many of this noise of false positives, but also it only detects it picks only a few voxels. And actually, even if you use some classifier that enforce some kind of special regularity on the pattern, it does not solve the problem, because the noise is actually more correlated in that case than the signal. So if you enforce correlation, you just don't do a better job. So the problem with the procedure proposed by Haufe is that the noise covariance is not manageable. It's not actually invertible when you use fMRI. So far we're stuck. I've redone the same simulation, but with a slightly different in the scenario. Now the true pattern is a bit smoother, and the noise is not as smooth. So you see that the T-map is a bit smoother. It's still a bit complicated with the ridge or SVM classifier to get the right pattern. You avoid now the bluish area around the red square, but still it's very noisy. The lasso does a better job, but now what comes is that the special regularization on the pattern do a good job at recovering the actual shape of the pattern. No, it's a bit like in a Bayesian analysis. When you put the right prior, you get the right answer somehow. Okay, so to go a bit deeper now into the problem. So when we do this kind of pattern analysis, we assume that the model is the following. You take your fMRI data X, you multiply by a certain pattern, so you combine the activity with of a certain pattern W0, which is the truth, and this generates your response Y, maybe with some noise. When you try to estimate the pattern from the data, you have a loss function that try to minimize the error, the prediction error, okay? So essentially, it's solving the problem y equal xw. But since x is not invertible, it has many more rows than columns. Sorry, columns than rows in that case. Then, of course, you will not be able to recover exactly w from y and x. So you need to penalize with some regularization j, so which will bias the solution. And this is where your prior come into play, and of course there is some kind of arbitrariness here. But remember that the W estimated cannot be equal to the ground truth. If we use a sparse model, people sometimes like sparse models because they think that it will give them a simpler explanation for a given phenomenon. The problem is that the sparse models cannot recover the correct support, the correct set of non-zero voxels, because essentially the fMRI data violate all the conditions to recover the correct sparse solution. And so the best that we can do so far is to introduce some relevant priors on the decoder. And so it has been also already described a bit by Jessica, I think. Like smoothness can help, or having small variations, so small total variation, which is a typical thing for image denoising, tends to work well. Okay, maybe you can think that I'm pushing too much here because, well, we could just do decoding on some predefined regions. And then we would not have all these issues, or not to that extent. Yes, but the devil is in the detail, because when you define an ROI, so we will know where the brain regions are, we just don't know where their boundaries are. So, it's very hard to specify correctly a brain region in terms of boundaries, especially if you do that across subjects. Now, if you do a poor ROI choice, well, you can have just suboptimal results. And there are some examples in the literature where people have been, repeating the same kind of poor choice just because they were replicating previous work, and until somebody comes and say, oh, actually, we should take another region to decode that. So there's a nice example in EEG by Guillaume Dumas and colleague. And the other issue with ROI selection, it has been actually discussed earlier, is p-hacking. Nothing guarantees that you define the region prior to data analysis. Okay, if we don't want to commit to one particular region, why not, varying the regions and in kind of searchlight approach where you feed the model to different voxels separately? It solves this problem to some extent, which is good, but with a high computational cost, especially if you need to do a permutation test to ensure that the results are significant, because you need to correct for multiple comparisons. Now that you're doing one test per voxel, typically, you don't know how to whether your results are significant or not without a test corrected for multiple comparisons. And also the typical issues with searchlight is that it's a bit short-sighted. It does just looks at the local effects and does not tell you about the large-scale interactions across the brain regions. Okay. So let's get back to our full brain analysis. And so we have the situation of vibration where different approaches will give different solutions. Actually, this is not such a new problem. It has been there in brain mapping since the beginning, even with simple univariate analysis. This is univariate analysis of the celebrated HAXB dataset, where you want to look at brain regions involved in face perception. So you could compare activity in response to faces to the resting, just to the baseline, and this will give you a certain brain map. Or you could compare it to the other conditions. There are 8 different conditions in this data set. So typically you would do the face minus the average of other conditions. It gives you a slightly different map. Or you could do even better a conjunction. You should look at the voxels that are more responsive to face than to tools, or face than animals, etc. Well, there's nothing that survives to this kind of procedure. So we're stuck, actually, with classical brain mapping, too. Now, if you do that with multivariate brain mapping, the nice thing that you can do this one against all classification, where you try to classify the response to faces versus all other possible categories, which is typically a bit better than doing just face versus baseline, face versus rest. So you obtain this kind of pattern. Of course, the pattern will depend on what comparison you do. Now, you can do that with different classifiers. And of course, these are rather bad news, because depending on the kind of classifier that you pick, you obtain a completely different solutions. They have some, I didn't put the scores, but they have some different scores. Not that different, actually. All these solutions are valid to some extent. So people have argued whether the coding of information of visual categories was local, clustered, distributed, etc. Well, the answer depends on your prior. It's very hard to get it. You cannot get it actually from decoding, basically. A point made by Jessica, so I'm just repeating quickly. Sorry. If you do the face versus rest classification. Well, it obtains this map, which is a bit messy, so you probably want to threshold it just to display the peaks in the classification. But no, this is forbidden, as Jessica said, because this is what you're presenting here is the pattern of the classifier, not the one that gave you the accuracy that you report. So if you want to obtain a brain map with blobs, the thing that you can do is either to do some prior voxel selection, like by screening, or using a sparse model, possibly with spatial regularization. So here I give two examples, which would solve this problem and obtain a more, maybe a better representation, but at least the accuracy of the model is actually the one that you report. One big drawback with this spatial regularization, like total variation minimization, is their cost. So to improve this, we have thought, and in Jean-Agnès' group, actually, they have worked on a similar line of different approaches to obtain this same kind of virtue. The idea here is to, for instance, have a sparse or non-sparse classifier. Actually, you don't take only one, you obtain several ones by using different splits of your population. So you just sample some of the variability of the possible patterns that you can obtain for this problem. You try to optimize over hyperparameters by picking the model that are optimize the classification in an inner loop, and then you average them. So this is called bagging, bootstrap averaging. And by bagging, you obtain a final model that is less noisy, essentially. And what we show in some experiment that we are currently publishing, you can see some previous version of this work already published, is that typically this bagging approach will improve slightly, but very slightly, the accuracy of the classifier. Where you really gain is the stability of the weight maps, because the aggregation, the averaging actually has a stabilization effect, because you have sampled some of the noise in your population. And so your model is a better consensus. And still, the computation time is intermediate between classical classifiers that are cheaper and the spatial regularization that are much more expensive. And also, it converges, these models converge faster to the asymptotic solution where you increase the size of the training set. So you get earlier, closer to the final solution when you look at more data. So for instance, in the phase versus place classification problem, so TV, total variation, minimization plus sparsity will give you a sparse maps with nice blobs, which is maybe something that you would expect. So it's less noisy than the classical support vector machine classification, which is much cheaper. So the bagging in that case, for instance, if you bag the L2 classifier, it will remove some of the noise. If you compare the two maps, you have removed some of the noise. You've obtained more smoother maps. Or you can even use some clustering step in the middle, which will create you even some more stable solution and also smoother. Okay, to finish the talk, I'm going to discuss a bit functional specificity, because so many people use these tools for brain mapping, cognitive brain mapping. So the first thing, if you want to characterize the response to houses, you probably don't want to compare only response to house images versus faces, but also to many different visual categories. Of course, this is true for all of brain mapping, but it has to be true for MVPA. And I would even suggest, whenever possible, to try to look across data sets, because when you have a certain set of stimuli, maybe your classifier is finding something in the stimuli, like the background or some information to classify. So if you can try to generalize to different data sets that have addressed a similar question, or try to see if the classifier is robust to these variations, because otherwise you may just be decoding some artifacts of your stimuli. Another point, it's actually a misconception that I found in the literature sometimes, is that people conclude from successful linear decoding of some information that the same information is encoded linearly in brain activity. And this is wrong. I'm going to give a counterexample of that. If you take the position of an object in the visual field, like just somewhere in the visual field, so you have the position as XY coordinates or in polar coordinates. So you can try to learn the position of an object from brain activity. So this is certainly not encoded linearly, but you can decode it linearly. So here is a sketch of the proof, if you like. So the visual field for the simplicity is just one-dimensional in that case. So we just have one spatial dimension, and you've got neurons or voxels, so with population receptive fields. So they are sensitive to the presence of an object in some part of the visual field. So it's a model of V1, if you like. So if an object is here in the visual field, you will have some neurons that will be activated, a bit the neighbors, and the others will not be activated. Now, if you just weight the response of the different neurons, you can perfectly decode the position of the object by just combining the activity of the neurons with these weights, you can perfectly read out the position of the object. But and this is linear decoding, but there is not a single neuron that encodes linearly the position of the object in the visual field. There is no neuron that will double its activity when the x coordinate of the object is doubled. So to wrap up now, MVPA relies on complex estimators, which imply that the results are often unstable under small perturbations, and interpretation needs caution. It's typically impossible to falsify encoding models with decoding, and it's also very hard to falsify the involvement of brain region with MVPA. And the patterns are very sensitive to model assumption and structured noise, I think, as I said in the previous talk. Remember that the thresholded pattern map is another model, so be careful with that. It's very important to state precisely what comparison is performed. And finally, I think fine-tuned priors can help improving MVPA. This is why we're doing this special regularization. So some of them are available in the Nylon library that we have developed for this kind of task, especially the total variation minimization. And we will add the bagging approach soon. So with this, I would like to thank my colleagues who took part in this study and the other partners who share the data, which is extremely important for the community. And thank you for your attention.
Thanks, Bertrand, for the great talk. So we have time now for questions and also for the open discussion, but perhaps we can start with questions for the talk. I think people really miss the coffee. Yeah, please.
So what happens when your structured noise follows the stimulus? Like if there's correlations in the noise that are really just spontaneous patterns that would happen anyway and they're correlated with the stimulus, like can you really tease that apart, or do you try to look at that?
No, I think you cannot do miracle. Maybe one thing that could occur if you have some good priors, like on the smoothness of the pattern, which can really distinguish the true signal from the noise. Hopefully, enforcing some prior will reduce the contribution of the noise and enhance the contribution of the truly predictive regions. But you never know in advance.
I guess that would be in the simulation. Like you were showing these blocks where you have, these four voxels are activated, but then the noise is correlated. So I guess you kind of showed that with the one where it was blurred. So you introduced some of those.
More questions? Please.
All right, thank you for a nice talk. I would like to challenge you a little bit on the ROI thing. So you argue that ROIs are bad because you're not able to distinguish which regions are where, but isn't that also a problem when you go to, for example, a standard space? Because brains, they are intrinsically different, and different noise structure will appear because you have differences in sulci and gyri. So it's just a different way of tackling the problem. But isn't that also a problem? Just full brain.
It's an interesting debate, actually a very old one, because people have argued about these questions, for 20 years. What should I say? No, what you say is basically true. Okay, we have a problem of between subject consistency, whether you report things in MNI space or whether you draw ROIs across subjects. You have the same issue. Just, ROI's definition is a bit problematic because the way you exactly place the boundary will have a role in the classifier. And, we all know where the empty region is in the brain, but nobody knows where it ends exactly. So when you give some MNI coordinates, you have some kind of ideas of where it is, but it's very hard to draw sharp and correct boundaries for regions. That's one point. And I think, okay, my philosophy, it's debatable. I think I prefer to discover the regions that are meaningful for some task from the data rather than imposing that a priori. Actually, that's an argument that Thirion used, for instance, to criticize ROI-based methods. He said at that time with SPM, you can define the shape of the clusters that are responsive to some task. While with ROI-based analysis, you are biasing essentially your results toward predefined structures.
That's true, but at the same time, I mean, when you go to a common space and you do some sort of smoothing also across subjects, you actually impose a difference in the overall covariance structure. So, I mean, at this point, when you go to a common space, you start to smooth across tissue types and so on. So, I guess we have to agree to disagree on at least, I mean, what's the most correct way to do it?
No, but it's true. Actually, it was some point which was implicit in my presentation, and I think it's good that you discuss that. Typically, the priors that tend to smooth the activity, they tend to work well, typically on between subjects, so across subject classification, because you want to have some smoothness due to the uncertainty created by the different spatial locations across subjects. When you are working within subject, smoothness is not so much useful because you can have a actually very spotty activity that is discriminative. But it's true that we cannot reason in the same way when you look at individual subjects, where you can really be very precise in the anatomical nature of the regions, whether you are on a part of a sulcus, etc., and across subjects where everything becomes a bit more fuzzy. Yeah.
I totally agree. Thanks.
More questions?
Yeah, I wanted to ask about your conclusion on the increased sensitivity claim. The problem that I always see with this claim is that on the one hand, yes, we have the intuition that MBPA should be able to uncover more variation related to the experimental changes. On the other hand, if we're talking about sensitivity, we would also have to talk about the statistical tests, and they are completely different statistical tests underlying univariate and multivariate analyses, or multivariate analyses don't use any statistical tests. So what does that claim even mean?
I think one way to bridge the two things is to think, okay, you could somehow do in a univariate or more univariate kind of spirit, or I would say parametric spirit, you could have several voxels together, for instance, and try to test whether the group of voxels displays activity or not. So using a hoteling t-test, for instance, which is a generalization of the t-test to multidimensional data. But then you have to take into account the covariance of the voxels. So once again, you're bad because voxels are highly correlated, so the inverse covariance will be a bit poorly conditioned, etc. So, but essentially, the classification accuracy is a kind of generalization of the hoteling t-test, where you don't bother that much about the covariance structure. You don't need to compute the covariance structure of the voxels, but on the other hand, you lose the ability to localize precisely the signal.
But would you agree that it doesn't make sense to speak about increased sensitivity if we don't use the same statistical test in both?
Yeah, no, typically that's true. We are testing something different.
Okay, thank you.
So more questions for Bertrand? If not, I suggest we open a discussion, perhaps having the speakers, and then people can, join and ask questions, just until we have a few minutes still, until 12.
kind of, if anybody has a comment.
I sit.
Yeah.
Hi. Thank you for all the talks until now. The question that I have is, a lot of the examples are used as VM. Is there work with random forests and how they perform? I've played around with those a little bit myself, but I couldn't manage to bring them down to identify voxels.
I have a poster from a student where we're using random forest and extra trees. So yeah, there is some work there.
I've played with them as well, but I guess it was kind of, for me, is sort of a pragmatic thing. It's probably kind of came out that I've played with them in certain data sets, and I've sometimes suggested to people to look into them if they're very interested in the importance measures that come out of random forests. But in general, I found them just a lot more hassle and not enough bang for the buck to make it worthwhile. But that's a very pragmatic, not a principled answer.
Yeah, you end up with very sparse solution as well. So well, it depends how you define the problem, and that was mainly used when you have smaller dimensions for your samples. So that work well when you have, say, 10,000 samples, 10,000 subjects, and only 20 features, and there that's super nice and super flexible. But here we are in the opposite way. We have 20,000 voxels and 100 samples, so it can make things a bit more complicated when you're treating each voxel individually in random picking. And so what works for some data outside neuroimaging is a bit more complicated. But I wouldn't rule it out completely, and you may maybe summarize your subject, say, with a model that prescribes its behavior or something with a few parameters, and maybe a linear discriminant thing like SVM will not work for that, and that will open up solutions. When it comes to imaging, I don't know, we're trying to use bits and tricks to use also atlases and selecting regions and stuff like that.
No, I fully agree. Essentially, random forests are not very good when P becomes larger than N. So P being the number of features, so the number of voxels in our case, and the N the number of samples. Because essentially the trees have to explore all the possible combinations of features. So when you have many more features than samples, it just doesn't scale well. Another comment is that what makes random forest attractive is that it's an ensemble method. It's a method that essentially averages weak classifiers, which are decision trees. And so in my talk, I try to present a way to ensemble linear models, which improves the good properties of improving the stability. But in that case, since they are linear models, they can be fit quite well on the high-dimensional data.
Maybe I can add a small bit. All the points raised by the previous speakers are all actually true, and they apply to many neuroimaging applications. But the applications are pretty diverse. In my own experience in building imaging biomarkers, I actually strongly recommend random forests for a few reasons. One being it's a multi-class by design. So you want to start thinking about multi-class, not just disease and healthy, because most of the times there is no single condition. And second of all, based on extensive amount of testing and large number of domains, there are papers actually I can send you. Random forest is shown to be just as good as anything out there, especially in multi-class, etc. So, and variable importance is actually very helpful because it can be mapped directly back to the original domain, so we can easily construct weight maps, for example. But it is true that when you have very high dimensional problems or the linear data inside, that SVM may be performing just as well in binary classification, with added problems that you don't have any class imbalance. So,
yeah, that's the experience I had as well. They work very well in general, but I just hadn't managed to go down to the voxel level. Thanks for all your responses.
I mean, you don't have to rely just on classifiers. There is a ton of very good feature selection or dimensionality reduction methods that can actually improve the accuracy quite a bit. So playing around with a few combinations of feature selection or dimensionality reduction with the classifier can take you to the next level of performance, but it's just a bit of a domain expertise and playing around. Always do proper cross validation, then you're good.
One question. Well, first of all, thank you for all the very great talk. A few of the speakers mentioned the weight maps, and I'm just curious on what is your thought on combining these, let's say you end up with within subject weight maps, what would be like setting aside the notion of sparsity, all the tweaks and the algorithm that will affect the actual space map, what is your thought on combining these maps at the group level and actually having like a legit way of doing this?
Do you want to I guess my answer would be don't do it. But I don't know if somebody else has a more involved, I just don't think, for some of the reasons, just with the stability and everything, and also you have the question of if you have, leave one run out and you have 5 runs, then each cross-validation fold within each person makes a new weight map, and if you do, and it's like, how do you combine those in a principled way? How do you go across people?
Can I return your question and what do you mean by combining at the group level? What is it that you are after? Exactly. If you answer that clearly, then we can give you a clear answer as well.
Yeah, that's yeah.
I think the general idea would just be to maybe go back to a notion that would be closer to like univariate method, like which voxels would at a group level contribute. So that wouldn't be a good idea.
You could have differences because normalization didn't work so well, or because the brain is slightly organized in a different way, or there is a different distribution of the noise or something.
Well, I would say it's still interesting to look at them if you're doing within subject, like classification, and then you're looking at all your different subjects, weight maps. Then it's good to see the overlap and see, kind of basically look at posteriori, like how stable your results are across subjects, because you have the fold problem, but obviously if you're doing different models for different subjects and you don't, for example, put them in M&I space or whatever, then you can try and look at the anatomical landmarks and see if they, if you use a sparse method, if they were used in all subjects or not. It's not really to relate directly to an SBM, but still to be able to look at the overlap and see if more of the noise was driving compared to more of the signal.
Maybe still my best advice in that case would be to try to train a classifier on, I don't know, a proportion of the subjects and then test on the other subjects. You rather want to test that directly to see if your model generalizes to new subjects.
But with some data, you can't really do that, though.
Yeah.
With ECOG, for example, you can't do that. So it's...
Sometimes it is indeed possible to combine them as long as they are commensurate. If you can turn it into a frequency score, for example, what I typically do is to keep an account of which voxel were selected to be included in the model. It's not exactly a weight per se in terms of activation or anything, but it's still useful to know that where the discrimination is coming from. So as long as the measure you compute is commensurate across the methods you're trying to combine, it should be okay. It's just a visualization map, right? So, and you can have actually very useful interpretation sometimes, depending on what you do with it.
Thank you.
My question is about the significance testing for the Searchlight MVPA, because I know that the permutation test is good, probably the best, but it's very time consuming and very often is not feasible in practice. So what do you recommend? What kind of other methods can we use for the Searchlight MVPA significance testing?
I don't see any real alternatives to that, at least not with standard multivariate measures. Those that are cross-validated, they have really weird distributions. I mean, In some books, you can still read comments like accuracies are binomially distributed. They clearly are not. There are special cases in which they can even be have bimodal distributions, or they have very long tails. I guess something you could get away with is to just compute a few permutations. In fMRI, permutations are hard anyway, so I think the only permutation I would say is really, really correct is the one where you exchange labels on run-wise estimates. Then you get 2 to the n-1 permutations, so something like 16 or at maximum 32, so it's not that many permutations anyway. And if you need smaller p-values, there are some ideas about extrapolating the tails of permutation distributions. There are some rules. Generalized Pareto distribution is one common model for tails of distributions. And there has been a paper by Knierenburg, for instance, where they applied that in order to extend the range of p-values for permutation tests with few permutations. But that, in my view, is basically it. If you want correct inference, you cannot get around doing the permutations. So maybe you have to do your analysis faster. The faster the single permutation is computed, the more you can do, right?
Yeah, okay, thank you. I just have a quick follow-up question. Why not just compute the null, or maybe you've done this, is the null for different voxels across, say, 10 voxels away that different? Like, why not just compute the null for, some subset? And then my actual question is, just generally speaking, it seems like these linear kernel SVMs are super popular. I'm wondering if that's because of interpretability, which has been kind of like a recurring theme, or you guys have some kind of prior that really, it really is a linear sort of transformation, or a linear kernel is the best explanation of the underlying sort of physiological separation of the MVPA patterns. So, thank you.
Well, I'll speak to a bit of that, and I think we all have opinions on part of that. So partly, linear SVMs, the fact that it's linear doesn't mean that the underlying signal is linear, and Bertrand can talk more on that. But linear SVMs tend to do better than some other algorithms when you have, they tend to be a bit, you can send 1,000 voxels in 5 examples, and maybe it'll work with linear SVMs. They can deal with the ill-posedness a little bit better and the redundant features a little bit better than some of the other algorithms. I would say is one reason that they're popular. It's definitely not, it's definitely incredibly case specific. I don't know if anybody else wants to add to that part of it.
Yeah, so for the linear versus nonlinear, as soon as the number of features becomes much larger than the number of samples, linear methods are recommended because they just work as well typically. Actually, nonlinear SVMs, if you look at it historically, it has been invented in the 90s where people had rather low dimensional data and they actually needed to increase the capacity of their classifier. Here in NeuroImaging, we are exactly in the opposite case where we already have representations of the data which are very high dimensional when you look at all the values per image. So we don't typically have this need to go to this nonlinear dimension expansion.
Yeah, and I think one practical but very important detail about SVM in general compared to Gaussian processes is that so they're pretty robust to noise and they give really good results compared to other methods that might be more complicated, and they're super fast compared to those methods. So when you run permutations and things, you can get results in a relatively reasonable amount of time, and it's usually like minutes. But if you run more complicated methods, including the MKL that we discussed about, or Gaussian processes, and so you can wait for days or sometimes weeks before you get the results from the permutations.
A follow-up question to the linear versus nonlinear. In linear versus, let's say, radial basis function, where people have nice pictures of two-dimensional, when there is a circular boundary. Is there like a particular way? Have you guys used something where if you have multiple dimensions, can you even look at the boundaries, hyperplane boundaries, in some manner or way that can sort of guide you to use linear versus nonlinear kernels?
Not possible over 3 dimensions.
Well, there are things like high dimension, there are high dimensional statistics, like distance concentration is one where you're trying to, where you're trying to get at the structure of your points in hyperspace. But I don't think there's any silver bullet. You can also do things like measure the distance of your points to the hyperplane, that kind of thing, to give you a bit of information. But
there's nothing like you can map it down to something.
You can. That may not be accurate in the high dimensional.
Yeah, actually, you can essentially map the gradient of your decision function. So there has been some work by DTU on this. It's published in NeuroImaging 2013, something like that.
Thank you.
Techniques like TSNE can actually give you very good representation, but it's just a reduced representation. So you have to keep in mind.
Everyone is hungry now? I mean, we're right on time. I don't know.
Maybe if there are no questions anymore, I think we can go for lunch. But just one thing, if you could, please don't forget to give feedback about the course, when you receive the emails. And please, it's quite important for us to be able to organize it again or not.